In this video, we're going to discuss Le Chatelier's principle. This is an idea about equilibrium that tells us what happens when something disturbs a chemical reaction at equilibrium. The general idea is if you are at equilibrium, if you have A in equilibrium with B, and we'll give it some K value for our efforts here of 10. Well, you will make some amount of each material. So let's just say we start at equilibrium already. We're going to have 10B and 1A. This means that when I have B divided by A, 10 over 1, I'm at 10. So this reaction by default will always have 10 times more B than it has A. Once it has reached this, I could have started, say, 11A and no B. Over time, it would have reproportioned, and it would have balanced out to here. Once at equilibrium, it will stay there indefinitely. Now, technically, some of this is always transferring at any given moment, but they're doing it at the same rate. This is important because I can disturb my reaction. I can go and add 50A. What this means is that at the moment of addition, I have 51A and 10B. Well, if I just plug that in right now, 10 divided by 51, that is not 10. 0.196. At the moment of addition of that extra A, I am no longer at equilibrium. There's just way more A around. There's way more chances for A to convert to B than there was a second ago when there was a single A around. In fact, there's 51 times more available. As a result, for a bit, my rate of A going to B is now massively greater than my rate of B going to A. They had been the same. I suddenly add way more A, and that rate now skyrockets. Well, this means there's going to be a change. Over time, I won't stay the same. They will alter now. I'm going to lose some A, I'm going to gain some B. Eventually, they'll reach equilibrium again. I'll get a little bit more rate from B, I'll get a little bit less rate from A as their concentration changes, and eventually they'll be equal. What will their new concentrations be where that is true? It's going to be 51 minus X, and it's going to be 10 plus X. Well, K must equal products of reactants, so 10 must equal 10 plus X divided by 51 minus X. Rearrange here. 510 minus 10X must equal 10 plus X. I can minus 10. I can add 10X. 500 must equal 11X. I can divide by 11. And what is my X value? 45.45. So what we'll find is that at equilibrium, we must now be 55.45 for our B, and we must be 5.545 for our A. And if we plug that in, 55.45 divided by 5.545 indeed is going to be 10. We've reached equilibrium again. Our actual concentrations are very different than they were originally. We were 10 and 1. We're now 55.5 and 5.5 and a half. The total amounts are greater because there's in total more molecules of stuff. I added 50 more molecules. There was only 11 to begin with. I should have way more stuff, but the ratio is still the same. It's still 10 times more products than reactants. What happened is when we disturbed the equilibrium, the balance of moving forward and reverse favored moving forward because of the increase in starting materials. This meant over time I increased my product and I decreased my starting materials. Indeed, I went from 51 down to 5.5 for my starting material, and I went from 10 up to 55.5 for my products. over time we saw that change. Reactions will naturally do this. A reaction disturbed from equilibrium will adjust to restore the equilibrium. This isn't a conscious choice, this is just a rates mechanic. Because we increased the concentration of A, we increased its rate. This favored moving towards product, favored increasing the product, favored reducing the starting material until those rates were equal again. Those rates will be equal when we're at equilibrium, which is when our concentrations in the mass action expression will equal our equilibrium constant. This means that any reaction, if you add extra product, is going to push towards starting material. If you add extra starting material, it's going to push towards product. What this means is that any change will be undone to the extent possible. Previously, we increased A, so the equilibrium reasserted itself by decreasing A. To do it, it has to move things to products. So to the extent possible represents the idea that our final concentrations were indeed different than our starting. But the idea is if you add a chemical, the mixture will try to decrease that chemical back down. If you remove a chemical, the mixture will try to increase that chemical back up. And the reaction can only do this by shifting products and reactants to one side or the other. This is the means by which it achieves countering the original change to the reaction. This actually allows us to do a few interesting things and exploit this behavior. If you can remove a product, more reactants will then move to make that product. So if you have a reaction that doesn't produce a lot of product normally, you can actually obtain all product if you can systematically remove it repeatedly along the reaction. Example here, Haberbash reaction. We need to make ammonia, but this is not actually a terribly favorable reaction. The K value is somewhere in the realm of 10 to the minus 5 at around 400 degrees Celsius. It doesn't favor making the product. The colder you can make this reaction, the more it favors the product actually, but then it runs slower. With the K disfavoring products so much, how can we obtain a reasonable amount of ammonia? If you simply put a bunch of nitrogen and hydrogen in a reactor, heat it up for a while, and then cool it quickly and try to separate out the ammonia, you'd get very little ammonia. We can cheat, however. If you set up a device where you have your reactor and you have a gas inlet for it, so the gas comes in. So we'll have our N2, we'll have our H2. They reach into the reactor, and some of them become NH3, but there's still plenty of N2 and H2 with it. These you pump out into another container, but this one you make cold. Well, the gas flows in, you have your N2, your H2, and your NH3, but if it's cold enough, ammonia will liquefy, leaving just N2 and H2 in the gas phase, which can be pumped back out, ran back through the system again. As that pure N2 and H2 goes back to the reactor, it doesn't see any ammonia. We've removed the ammonia. We can drain that ammonia out through a little spigot off to another system. Liquefying the ammonia reduces the product. It makes this go away. If we reduce the product, if we remove it, the equilibrium is going to push towards trying to replace it. So more nitrogen and hydrogen will react. We effectively trick the equilibrium into thinking we never have ammonia. It simply consistently attempts to produce product because the ammonia is never available to go backwards. In effect, we have a rate forward, but we keep removing ammonia, so we have no rate reverse. Other types of ways we exploit this: when esters are made. If you do organic chemistry, an ester is just a molecule that starts with a carboxylic acid and an alcohol. These will react to make an ester, which is a carbon, double bond oxygen, and single bond oxygen, and then those go off to more carbons. But this also makes water, and this is an equilibrium reaction. If you try to make the ester by mixing a carboxylic acid and some alcohol together, you'll make some ester and some water, but then as you build it up, the reverse reaction will start breaking it apart. Two ways we cheat is if you can pull water out of solution. There are various minerals and compounds that absorb water quite nicely, and so every time the water gets produced, it gets absorbed by something and disappears from the solution. Well, if you don't have water, you can't do the reverse reaction. The concentration looks zero. And so even as we keep reacting and piling up more and more and more of our ester, as long as we keep removing the water, it can never go backwards. Other ways we trick this is to flood it with tons of alcohol. Maybe you have 100 carboxylic acids, but if you have 1,000,000 of the alcohol, you're just really favoring pushing across. Even if you get a reasonable amount of water, you still have so much alcohol, just favors shoving to the other side. There's a few tricks we can do. I can massively increase one side to force it to push to the other side to try to get rid of that increase. Or I can remove a component to again force it to move in that direction to replace the removed component. Le Chatelier's principle is just a descriptive idea of what's going on when a reaction is at equilibrium and then suddenly gets disturbed. As a chemical is added or removed, what is the present balance of rates at that moment of change? Which direction is the reaction then going to favor? And so as it does that over time, what will the new concentrations be once we reach equilibrium? Even if we're not trying to solve out exactly what those concentrations are, we can see what the changes will do to an equilibrium reaction. Adding some chemical will result in material moving away from that side of the reaction to try to reduce that chemical back down. Removing a chemical result in the reaction moving towards that side of the reaction to recreate the lost chemical.